Okay, so welcome back. Today we'll try to cover optimizers, and to begin with, we're going to watch Andrew Ng's videos on gradient descent, RMSProp, and Adam, and then we'll try to complete uh, this section of optimization. Okay, let's begin.
Momentum or gradient descent with momentum that almost always works faster than the standard gradient descent algorithm. In one sentence, the basic idea is to compute an exponentially weighted average of your gradients and then to use that gradient to update your weights instead. In this video, let's unpack that one sentence description and see how you can actually implement this. As a motivating example, let's say that you're trying to optimize a cost function which has contours like this. So the red dot denotes the position of the minimum. Maybe you start gradient descent here. And if you take one iteration of gradient descent, either batch or mini batch gradient descent, maybe you end up heading there. But now you're on the other side of this ellipse. You and if you take another step of gradient descent, maybe you end up doing that. And then another step, and so on. And you see that gradient descents will, sort of take a lot of steps, right? And just slowly oscillate toward the minimum. And these up and down oscillations slows down gradient descent and prevents you from using a much larger learning rate. In particular, if you were to use a much larger learning rate, you might end up overshooting and end up diverging like so. And so the need to prevent the oscillations from getting too big forces you to use a learning rate that's not itself too large. Another way of viewing this problem is that on the vertical axis, you want your learning to be a bit slower because you don't want those oscillations. But on the horizontal axis, you want faster learning, right? Because you want it to aggressively move from left to right toward that minimum, toward that red dot. So here's what you can do if you implement gradient descent with momentum. On each iteration, or more specifically, during iteration t, you would compute the usual derivatives dw, db. I'll omit the superscript square bracket else, but you compute dw, db on the current mini batch. And if you're using batch gradient descent, then the current mini batch would be just your whole batch. And this works as well for batch gradient descent. So if your current mini batch is your entire training set, this works fine as well. And then what you do is you compute v dw to be beta v dw plus 1 minus beta dw. So this is similar to when we're previously computing v theta equals beta v theta plus 1 minus beta theta t. Right? So it's computing moving average of the derivatives for w you're getting. And then you similarly compute vdb equals that plus 1 minus beta times db. And then you would update your weights using w gets updated as w minus the learning rate times. Instead of updating it with dw with the derivative, you would update it with v dw. And similarly, b gets updated as b minus alpha times v db. So what this does is smooth out the steps of gradient descent. For example, let's say that the last few derivatives you computed were this. If you average out these gradients, you find that the oscillations in the vertical direction will tend to average out to something closer to 0. So in the vertical direction, where you want to slow things down, this will average out positive and negative numbers, so the average will be close to 0. Whereas on the horizontal direction, all the derivatives are pointing to the right in the horizontal direction, so the average in the horizontal direction will still be pretty big. So that's why with this algorithm, with a few iterations, you find that the gradient descent with momentum ends up eventually just taking steps that are much smaller oscillations in the vertical direction, but are more directed toward the horizontal, to just moving quickly in the horizontal direction. And so this allows your algorithm to take a more straightforward path, or less to damp out the oscillations in its path to the minimum. One intuition for this momentum, which works for some people and not for everyone, is that if you're trying to minimize a bow shape function, right? This is really the contours of a bow, because I'm not very good at drawing. But if you're trying to minimize this type of bow shape function, then these derivative terms you can think of as providing acceleration to a ball that you're rolling downhill, and these momentum terms you can think of as representing the velocity. And so imagine that you have a bow and you take a ball and the derivative imparts acceleration to this little ball. As the little ball is rolling down this hill, right? And so it rolls faster and faster because of acceleration. And beta, because this number a little bit less than 1, displays a rho of friction, and it prevents your ball from speeding up without limit. But so rather than gradient descent just taking every single step independently of all previous steps, now your little ball can roll downhill and gain momentum. Right? It can accelerate down this bow and therefore gain momentum. I find that this ball rolling down a bow analogy, it seems to work for some people who enjoy physics intuitions, but it doesn't work for everyone. So if this analogy of a ball rolling down a bow doesn't work for you, don't worry about it. Finally, let's look at some details on how you implement this. Here's the algorithm, and so you now have two hyperparameters, the learning rate alpha as well as this parameter beta, which controls your exponentially weighted average. The most common value for beta is 0.9. We're averaging over the last 10 days temperature, so this is like averaging over the last 10 iterations gradients. And in practice, beta equals 0.9 works very well. Feel free to try different values and do some hyperparameter search, but 0.9 appears to be a pretty robust value. Well, and how about bias correction, right? So do you want to take VDW and VDB and divide it by 1 minus beta to the t? In practice, people don't usually do this because after just 10 iterations, your moving average will have warmed up and there's no longer a bias estimate. So in practice, I don't really see people bothering with bias correction when implementing gradient descent with momentum. And of course, this process is initialized with VDW equals 0. Note that this is a matrix of zeros with the same dimension as DW, which is the same dimension as W, and VDB is also initialized to a vector of zeros with the same dimension as DB, which in turn has the same dimension as B. Finally, I just mentioned that if you read the literature on gradient descent with momentum, often you see it with this term omitted, with this 1 minus beta term omitted. So you end up with VDW equals beta, VDW plus VDW. And the net effect of using this version in purple is that VDW ends up being scaled by a factor of 1 minus beta, or really 1 over 1 minus beta. And so when you're performing these gradient descent updates, alpha just needs to change by a corresponding value of or 1 over 1 minus beta. In practice, both of these will work just fine. It just affects what's the best value of the learning rate alpha. But I find that this particular formulation is a little less intuitive because one impact of this is that if you end up tuning the hyperparameter beta, then this affects the scaling of VDW and VDB as well. And so you end up needing to retune the learning rate alpha as well, maybe. So I personally prefer the formulation that I've written here on the left rather than leaving out the 1 minus beta term. But so I tend to use the formula on the left, the printed formula with the 1 minus beta term. But for both versions, having beta equals 0.9 is a common choice of hyperparameter. It's just that alpha, the learning rate, will need to be tuned differently for these two different versions. So that's it for gradient descent with momentum. This will almost always work better than the straightforward gradient descent algorithm without momentum. But there's still other things we could do to speed up your learning algorithm. Let's continue talking about these in the next couple videos.
Okay.
Another algorithm called RMSProp, which stands for root mean square prop. They can also speed up gradient descent. Let's see how it works. Recall our example from before that if you implement gradient descent, you can end up with huge oscillations in the vertical direction, even whilst trying to make progress in the horizontal direction. In order to provide intuition for this example, let's say that the vertical axis is the parameter B and the horizontal axis is the parameter W. Right? It really could be W1 and W2 or some of the standard parameters, but let's name this B and W for the sake of intuition. And so you want to slow down the learning in the B direction or in the vertical direction and speed up learning, or at least not slow it down, in the horizontal direction. So this is what the RMSProp algorithm does to accomplish this. On iteration T, it will compute, as usual, the derivative dW dB on the current mini batch. So I was going to keep this exponentially weighted average. Instead of VDW, I'm going to use new notation SDW. So SDW is equal to beta times their previous value plus 1 minus beta times dW squared. I sometimes write this dW star star 2 to denote the exponentiation. Let's write this as dW squared. So for clarity, this squaring operation is an element-wise squaring operation. So what this is doing is really keeping an exponentially weighted average of the squares of the derivatives. And similarly, we also have SDB equals beta SDB plus 1 minus beta dB squared. And again, the squaring is an element-wise operation. Next, RMSProp then updates the parameters as follows. W gets updated as W minus the learning rate. And whereas previously we had alpha times dW, now is dW divided by square root of SDW. And B gets updated as B minus the learning rate times, instead of just the gradient, this is also divided by, now divided by SDB. So let's gain some intuition about how this works. Recall that in the horizontal direction, or in this example, in the W direction, we want learning to go pretty fast, whereas in the vertical direction, or in this example, in the B direction, we want to slow down or to damp out the oscillations in the vertical direction. So with these terms, SDW and SDB, what we're hoping is that SDW will be relatively small, so that here we're dividing by a relatively small number, whereas SDB would be relatively large, so that here we're dividing by a relatively large number in order to slow down the updates in the vertical direction. And indeed, if you look at the derivatives, these derivatives are much larger in the vertical direction than in the horizontal direction. So, the slope is very large in the B direction, right? So with derivatives like this, this is a very large dB and a relatively small dW, because the function is sloped much more steeply in the vertical direction, that is in the B direction, than in the W direction, than in the horizontal direction. And so dB squared will be relatively large, so SDB will be relatively large, whereas compared to that, dW will be smaller, or dW squared will be smaller, and so SDW will be smaller. So the net effect of this is that your updates in the vertical direction are divided by a much larger number, and so that helps damp out the oscillations, whereas the updates in the horizontal direction are divided by a smaller number. So the net impact of using RMSProp is that your updates will end up looking more like this, right? That your updates in the vertical direction get damped out, but then horizontal direction it can keep going. And one effect of this is also that you could therefore use a larger learning rate alpha and get faster learning without it diverging in the vertical direction. Now, just for the sake of clarity, I've been calling the vertical and horizontal directions B and W just to illustrate this. In practice, you're in a very high dimensional space of parameters. So maybe the vertical dimensions where you're trying to damp out oscillations is some set of parameters W1, W2, W17, and the horizontal dimensions might be W3, W4, and so on, right? And so the separation is a W and P is just for illustration. In practice, dW is a very high dimensional parameter vector, dP is also a very high dimensional parameter vector, but the intuition is that in dimensions where you're getting these oscillations, you end up computing a larger sum or weighted average for these squares of derivatives, and so you end up damping out the directions in which there are these oscillations. So that's RMSProp, and it stands for root mean squared, because root mean square prop, because here you're squaring the derivatives and then you take the square root here at the end. So finally, just a couple last details on this algorithm before we move on. In the next video, we're actually going to combine RMSProp together with momentum. So rather than using the hyperparameter beta, which we had used for momentum, I'm going to call this hyperparameter beta2, just to not clash, have the same hyperparameter for both momentum and for RMSProp. And also to make sure that your algorithm doesn't divide by 0. What if square root of SDW, right, is very close to 0, then this thing could blow up. Just to ensure numerical stability, when you implement this in practice, you add a very, very small epsilon to the denominator. Doesn't really matter what epsilon is. You use 10 to the negative 8 would be a reasonable default, but this just ensures slightly greater numerical stability that, for numerical round off or whatever reason, that you don't end up dividing by a very small number. So that's RMSProp, and similar to momentum, has the effects of damping out the oscillations in gradient descent and mini batch gradient descent, and allowing you to maybe use a larger learning rate alpha, and certainly speeding up the learning speed of your algorithm. So now you know how to implement RMSProp, and this will be another way for you to speed up your learning algorithm. One fun fact about RMSProp, it was actually first proposed not in an academic research paper, but in a Coursera course that Jeff Hinton had taught on Coursera many years ago. I guess Coursera wasn't intended to be a platform for dissemination of novel academic research, but it worked out pretty well in that case. It was really from the Coursera course that RMSProp started to become widely known, and it really took off. We talked about momentum, we talked about RMSProp. It turns out that you put them together, you can get an even better optimization algorithm.
RMSProp.
Learning, many researchers, including some very well-known researchers, sometimes propose optimization algorithms and show they work well in a few problems. But those optimization algorithms subsequently were shown not to really generalize that well to the wide range of neural networks you might want to train. So over time, I think the deep learning community actually developed some amount of skepticism about new optimization algorithms. And a lot of people felt that gradient descent with momentum really works well. It's difficult to propose things that work much better. So RMSProp and the Adam optimization algorithm, which we'll talk about in this video, is one of those rare algorithms that has really stood up and has been shown to work well across a wide range of deep learning architectures. So this is one of the algorithms that I wouldn't hesitate to recommend you try because many people have tried it and seen it work well on many problems. And the Adam optimization algorithm is basically taking momentum and RMSProp and putting them together. So let's see how that works. To implement Adam, you would initialize VDW equals 0, SDW equals 0, and similarly VDB SD compute DW DB using current mini batch, actually weighted average. So VDW equals beta, but now I'm going to call this. So this is exactly what we had when we're implementing momentum, except that I've now called the hyperparameter beta 1 instead of beta. And similarly, you have VDB as update as well. So now you have a different hyperparameter beta 2 plus 1 minus beta 2, dw squared. And again, the squaring there is element-wise squaring of your derivatives dw. And then SDB is equal to this, like update with hyperparameter beta 1, and this is the RMSProp like update with hyperparameter beta 2. In the typical implementation of Adam, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dw equals V dw divided by 1 minus beta 1 to the power of t, if you've done t iterations, and similarly v db corrected equals v db divided by 1 minus beta 1 to the power of t, and then similarly you implement this bias corrections, db corrected. Finally, you perform the update. So w gets w, or maybe v dw corrected, but now we add in the RMSProp portion of this, so we're also going to divide by square root of s dw corrected, divided by square root s corrected db plus epsilon. And so this algorithm combines the effect of gradient descent with momentum together with gradient descent with RMSProp. And this is a commonly used learning algorithm that's proven to be very effective for many different neural networks with a very wide variety of architectures. So this algorithm has a number of hyperparameters. The learning rate hyperparameter alpha is still important and usually needs to be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dw, right? This is the momentum-like term. The hyperparameter for beta 2, the authors of the Adam paper, inventors of the Adam algorithm, recommend 0.999. Again, this is computing the moving weighted average of dw squared as well as dp squared. And then epsilon, the choice of epsilon doesn't matter very much, but the authors of the Adam paper recommended 10 to the minus 8. But this parameter, you really don't need to set it, and it doesn't affect performance much at all. But when implementing Adam, what people usually do is just use the default values of beta 1 and beta 2, as well as epsilon. I don't think anyone ever really tunes epsilon. And then try a range of values of alpha to see what works best. You can also tune beta 1 and beta 2, but it's not done that often among the practitioners I know. So where does the term Adam come from? Adam stands for adaptive moment estimation. So beta 1 is computing the mean of the derivatives. This is called the first moment. And beta 2 is used to compute exponentially weighted average of the squares. And that's called the second moment. So that gives rise to the name adaptive moment estimation. But everyone just calls it the Adam optimization algorithm. And by the way, one of my long-term friends and collaborators is called Adam Coates. As far as I know, this algorithm doesn't have anything to do with him, except for the fact that I think he uses it sometimes. But sometimes I get asked that question. So just in case you're wondering. So that's it for the Adam optimization algorithm. With it, I think you really train your neural networks much more quickly.
Okay, so I think let's do this. Let's open it. I need to make a copy. I think I do. or maybe I don't. Okay, so the setup is done. Doing all the inputs here. Done. So here we are, optimizers. Went through these 3 videos. Right. Uh, shampoo. Cool. Right, so this is the patch gradient descent. It's a loss over the entire data set. Rarely used because data sets are not small. Then you have stochastic gradient descent, loss in a random selected example. Expectation is the right direction. Doesn't parallelize well, so nope. And then you have something in between, mini patch gradient descent. Okay. Okay. Hmm. Maybe we can get to this sometime. Okay, we'll get back to that maybe. Hmm. Okay, optimizes two parameters using gradient descent, the value of the function. Hmm. Hmm. Mm, oops. Yeah, and we need to initialize an optimizer. What's the, yeah, um, LR. The gradient. Uh, Step 0 the gradients. Uh, then finally we return XY list. Yeah, let's run this. Oops. Should return a tensor. Hmm. So if you see in this case, the blue case where learning rate is 0.02, momentum is 0.99. Hmm, close enough. Uh, yeah, so I guess the point here is that um, right, along the ridges, the gradient is much bigger in this direction than the y direction, and we'll have to reduce our learning rate, but that will slow down learning. Hmm. Okay, let's move on to the next section. Build your own optimizers. Hmm. Right, the first one is to implement SGD. We have learning rate, parameters we won't update, momentum, we have weight decay, we have bias. Hmm. Mm, so I need to do one step of this and gradient would be something I already have with dot grad. So and then we have lambda is rate decay. We apply rate decay to the gradient. Hmm. So this is not modifying the param.grad in place. So that's what we want. And if we have momentum, then basically calculate can I do this? P of I equals dot u times I two. Oh, okay. Here using the other version where we don't this. And then finally we update. And then finally update param. No attribute grad string object. Let me remove this. Alright. I think I'll do at least one more. Yeah, I think I'll just at least do this. Let's do RMSProp. I want to see what's Python version is like. PyTorch version. There also is centered. Which we can take as false by default. So let's do this. And then we get our grad for the param. And if we have it, okay, then we do, yeah, we do not want to modify grad. We do k times param. we want to update the square average, the and the way we do it is this, and then we do times g squared. Hmm. Right, so why do we do this? I don't think we need to do that. And then we do if you uh 2 by and then hmm, pattern minus equals clearing rate times p, else we have pattern rate times basically this. Hmm, think this is it. I don't have 20k. What's it called? Lambda. Okay. Yeah, I think this is a good time to stop here. I don't know if I'll do the remaining ones. It seems pretty similar to been doing so far. What's this? Okay, there's some analysis of different optimizers for different hyperparameter values. And this small section on parameter groups. Hmm. Okay, so yeah, I think I'll stop here. Next time, I think I might implement Atom and then move on to these two subsections, plotting optimizers and handling parameter groups, then also cover weights and biases. Yeah, and then the final section, I think it'll have to be outside collab. So yeah, that should not be a problem. Mostly, think we can stop now.